All right, now the next part of naming is what happens if you have an ether that's much more complicated, meaning here's the ether part. I have the oxygen. I have an isopropyl group on one side, but then on the other side I have something much more complicated than just a simple methyl, ethyl, isopropyl, terbutyl, any of those easy names. I have something much more complicated. What happens now is this group now becomes a substituent. All right, and you name this according to the rules that we previously learned. Look for the functional group. In this case, my longest continuous chain is an alkane. So this is my longest continuous chain now, is this part right here, which is hexane. Okay, and then you number it like how we've learned, number it from the side closest to a substituent. So here's carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. I've got a chlorine substituent, and I have a isopropoxy, because now the substituents are what's called an alkoxy group. All right, so you name it, so it's an isopropyl, so it's isopro-oxy. You just put the oxy at the end of it. Okay, so the name of this would be 3-chloro, because chlorine alphabetically is before the iso, and then isopropoxy hexane. Okay, so the previous example, if your groups are easy, you just name it whatever, ethyl, methyl, ether. But if it's much more complicated, then you use the oxy way of naming it. We'll do a lot of these problems in class. Also, your homework will have a lot of them. The next one are cyclical ethers. Cyclical ethers are it's a type of compound which is called a heterocycle. Heterocycles are basically cyclical compounds that have atoms in it other than carbon. So it will have an oxygen, a nitrogen, a sulfur, something other than carbon. In this case, obviously, they're oxygens, but when we get to the amine chapter, you'll have ones that have nitrogens in them. All right, so in this case, oxygen is part of your ring. So a heterocycle is not just a ring with oxygen. It could be any type of non-carbon group. In this case, they're just oxygens. All right, epoxides. We've learned about epoxides. There are 2 carbons with an oxygen. Oxirane is kind of more of the family of the functional group. I don't really want you to worry about that too much. I really want you to know the epoxide. A 4-member ring is called oxetane. You do not have to know this. We won't be seeing these compounds. But a 5-membered ring, furans are very common. We have learned about THF. This compound right here is THF, which, if you remember, THF stands for tetrahydrofuran. Okay, which this compound right here is furan. That's furan with the double bonds. If you add hydrogens to it to hydrogenate, you're going to be adding 4 hydrogens. 2 hydrogens here and 2 hydrogens here. That's where the tetrahydro comes from, and then furan. So this, where it's all single bonds, is what's called tetrahydrofuran, because you hydrogenated furan. Okay. 5-member ring are called pyrans, and the 6-member rings with 2 oxygens is a dioxane. Really, furan and epoxides are the 2 that I want you really to know more. The other ones are not that common, and we're not going to see them too much. You don't have to know how to name compounds with them. You just need to know what they are. Furan and THF, or tetrahydrofuran, and epoxides. You know what epoxides are. All right. Naming epoxides, there's really 2 ways. Again, there's the kind of the common name. If you just have an epoxide on your group, no other groups, if it's not complicated, you just have a group, in this case I have a cyclohexane with an epoxide coming off of it. You name it based off of the starting alkene it comes from. Okay, remember we learned epoxides come from alkenes. So this is a this came from cyclohexene and ended in oxide. So if, let's say, you have a compound that looks like this, all right, why don't you put this on pause and name the compound? Put it on pause now. Welcome back. The way that you would name this is a 1, 2, 3, 4, 5, 6, 7-member chain. So this would be called, how you name this is heptene oxide. All right, heptene oxide. Okay, how do I get that? Well, it comes from heptene, or the heptene, where the double bond is on the 2 and the 3 carbon. So if you remember naming alkenes, your alkene that it comes from, in this case, would be this, which is heptene. Happens to be the cis, but let's not worry about the cis and trans. So it's heptene. This compound is called heptene, and then you just end it in oxide. So that's how the more the common name. Okay. However, if you have groups other, like hanging off of your chain, these are just all carbons and hydrogens. But what happens if you have another methyl group hanging off of this, or a chlorine group, or whatever? This now is a substituent. When your epoxide becomes a substituent, you name it epoxy. So epoxy is the name for the substituent. It's the equivalent as the ethoxy or the alkoxy group. All right. So on this one, I have a methyl group on the 4 carbon, okay, and then I have my epoxide group on carbons 1 and 2. So here you say, on 1 and 2, I have the epoxy group. So 1, 2 epoxy, 4 methyl, cyclohexane. My parent now is a cyclohexane. Okay. On this compound, my parent is my hexane group. It's those 6 carbons. That's your parent. And what do you have hanging off of it? I have an methoxy. That's your methoxy group. And then you have your epoxide group. So that's a 2,3 epoxy group. So cis, all right, the reason it's cis is because notice your epoxide is cis, because this could be trans as well. All right, so this is cis 2,3 epoxy 4 methoxy hexane. Okay, so that's how you would name epoxides. You either have the more common way, if you don't have any complicated rings or anything like that. I'm sorry, if you don't have any complicated groups hanging off of it. But once you start getting things hanging off of it, it's no longer easy to name it. You have to use it as an epoxy group. Okay, like I said, best way to do naming is just do practice problems, and we will do some in class. We're going to skip 14.4. 14.4 in your book is about the mass spec and the IR of ethers. We've kind of done that last semester, so we don't need to do that again. 14.5 is the Williamson ether synthesis. This is the first reaction of how to make an ether. This is something we've already learned. We learned this when we did the SN2 chapter. All right, so the way that you do a Williamson ether synthesis is by an SN2. All right, you have your alkoxide. This is called an alkoxide. Anytime you see an oxygen with a negative charge, that group is called an alkoxide group. So you have your alkoxide. You're doing straightforward SN2 attack, followed by the leaving of your halogen. All right, the arrow is already in here, but thought I'd do it again. And you form your ether. And this is what's called a Williamson ether synthesis. Williamson, I guess he got his name after this, even though this is just a straight SN2 reaction. You have your strong nucleophile. Usually you need a unhindered base, right there, unhindered primary alkyl halide. Tosylates, we learned about tosylates last semester, OTS. These were groups other than halogens. You have an OTS group. If you don't remember those, look at your notes from last semester. Otherwise, just ask me in class and we can talk about those. All right, and the alkoxide, remember, is formed by taking an alcohol and adding either sodium metal or potassium metal or sodium hydride to it to form the negative charge. All right, so just to kind of remind you, if you have an alcohol and then add, let's say, like sodium metal to it, all right, remember you get the alkoxide, O minus, plus hydrogen as a gas. Okay, and you have your sodium ion, sodium plus, as the counter ion of that O negative. Here are some examples of Williamson ether synthesis. Here you have sodium plucking off the hydrogen to form the O negative. And then here's your OTS group. Here's your tosylate group that we talked about. Very good leaving group. So it's basically also SN2. Once you form your O minus, this oxygen goes ahead, adds to that carbon, and kicks out your OTS group. Okay. Here's just another way, classic SN2 with an alkyl halide. Your sodium hydride plucks off the hydrogen, forms the negative, and then goes ahead and adds to the methyl iodide. Notice in each case how your halides or your tosylate groups are the least substituted. Notice here I have a primary tosylate. Here I have a methyl iodide. My alcohol is secondary. The alcohol is secondary. But the alcohol is on the more substituted position where your electrophile is the least substituted. Make sure you keep that in mind because that's what SN2 reactions work best as. Here's an example of a phenyl ether. Same type of thing, Williamson ether synthesis. However, your hydrogen on a phenyl ring or on a phenol, this is a type of a phenol. All right, remember phenols is an aromatic ring with an alcohol hanging off of it. All right. These hydrogens are much more acidic than a regular alcohol. All right, and that's because when you pluck them off, you form a negative charge on those oxygens. And what is so special about forming a negative charge on a phenol that makes it much more acidic? All right, well, the answer is resonance. If you said resonance, good job. So if I put my lone pairs here, this negative charge can resonate through the molecule. Okay, so these hydrogens are much more acidic, especially now you have a nitro group, which is an electron withdrawing group. We'll learn much more about these when we get to the aromatic chapter. So you just need to use hydroxide. You don't have to use sodium metal or potassium or a hydride. Those are very strong as bases. Hydroxides are good enough to pluck off these hydrogens because these hydrogens are so much more acidic. Okay, so you can form your O negative, which is sodium hydride. And then once you form the O minus, it can then attack your primary alkyl halide. All right, so phenoxide, this is called a phenoxide, are easily produced because the alcohol proton is more acidic. I just said this, didn't realize that these were already in the notes. And the phenyl halides and tosylates cannot be used in this synthesis method. Yeah, so obviously I can't have this as the iodide or the tosylate. Okay, if this was the iodide, then I'd be attacking an sp2 carbon, and we know that SN2s do not occur on sp2 carbons, they occur on sp3. So your alcohol, your OH group, has to be on the aromatic ring, not on the alkyl part of it. Okay?